Limits and continuity. So we've kind of, in this particular methods 3 and 4, we've only got to have an understanding and some fairly obvious rules on how to handle them. So notation, we know the notation. We've seen this loads and loads before, especially when we do that differentiating by first principles. What do you think limits are used for? So talk to yourself about it. So as x approaches infinity, the limit of the function is 4. And that's the function 1 over x plus 4. So if you think if that becomes infinity, 1 divided by infinity is as close to 0 as possible, isn't it? So polynomials, when we've got the truncus and the rectangular hyperbolas, all those sort of things, we're going to be looking at limits linked to asymptotes. So we'll have a look at those. So first one seems a bit ridiculous, but we can actually write it this way. So the limit as x approaches 2 of 3x squared is just 12. Yep, and we say that's how we need to, sort of the terminology that we need to use. As x gets closer and closer to 2, the value of 3x squared gets closer and closer to 12, even though it has actually exactly is 12, isn't it? So nothing special there. This one here, a little bit different. So if we think about that function, we can factorize the top. And when we factorize the top, we can cancel those two. So we just get 2x minus 1, as long as x does not equal to 2. So don't forget, x cannot equal to 2. It doesn't really make any difference to this, but it does make a difference to the original function. So now we can just say the limit is going to be 2 times 2, which is 4, take away 1, which is 3. Now, when we draw the graph, okay, what we're really doing, so if you think drawing this graph would be a pain, wouldn't it? When we've done the factorizing, we're just drawing the graph 2x minus 1, year 7 work. But what we have to remember to do is there's no value when x is 2. So x cannot equal to 2. So there's no value. So we've got to be really careful, especially you messy people. We've got to have a circle there and it can't be colored in. So if we look at this example, again, a little bit more detail. Okay, if we look at we can actually put a table in, say, okay, we know that x can't equal 2, yeah? So we're going to go x is less than 2. So x is less than 2. So when x is 1.7, we get that answer. 1.8, that answer. As x gets closer and closer to 2, the answer gets closer and closer to 3. Similarly, if we do it for when x is greater than 2, so 2.3, 2.2, 2.1, you can see as x gets closer and closer to 2, the answer gets closer and closer to 3. So it happens when x is less than 2 and when x is less and greater than 2. So there's two different sides, and we'll look at that in more detail. So there's just some notes for you. So here's a nice simple one, the first one. So the limit as h approaches 0 of 3h plus 4, you can write it and split them up. I mean, we can do this one in our head, but we can just split them up. Limits as h approaches 0, this one here becomes 0. In fact, there's no h in that, so it doesn't affect it at all. So the answer is just 4. This one here. Okay, well, I'm thinking that one, hopefully this one will factorize. So we can just cancel those and we'll just end up with x. So the limit as x approaches 3 of x is just going to be 3, yeah? Left and right limits. So this is what I was talking about before. You can approach it from one side or the other side. So just the way it's written, as x approaches a from the positive side, as x approaches a from the negative side. And this is like the same as this, yeah? Coming from one side, coming from the other side. Here, we end up with the same value 3, whichever side we come from. Not always the case though. So let's have a look at these piecewise things. This bit here, greater than or equal to 0, so it's coloured in. Less than or equal to 1, not coloured in. When x is 5, it equals 1, so it's just coloured in. Between 1 and 2, so it's it's greater than 1, not coloured in. Less than or equal to 2, coloured in. Rectangular hyperbola, so this one here, we can see that as x approaches 0, so as x approaches 0, it approaches infinity. And if we do it from this side, as x approaches 0 from this side, so this is from the positive side, it approaches infinity. As it approaches from the negative side, it still approaches infinity. So when we look at the rectangular hyperbola though, so that's your truncus, so that's just your 1 over x, you can see that as x approaches 0 from the negative side, it approaches negative infinity. As x approaches 0 from the positive side, it approaches positive infinity. What about at a particular point? Look at the particular point. At a particular point, can be drawn through a point of coordinates without a break. Look at this. There's a break, isn't there? So let's have a look at this first one. State the values for x for which the functions below have discontinuity. So it's continuous, discontinuous at x equals 1. The reason being, the value of the function f of 1 is 3. Let's have a look at the limit. So as we approach 1 from the negative side, so approaching 1 from the negative side, the limit is 2. As we approach it from the positive side, the limit is also 2. So that's why it's discontinuous. Look at the second one. At -1 first, we're looking at -1 first. So at -1, the function at -1 is 2. So the limit, so if we come to -1 from here, it's 2. Perfect. As we come from -1 this way, we can see that it's actually approaching minus infinity. It's okay when we approach it from this side, from the negative side, but when we approach it from the positive side, it actually approaches negative infinity. And also with this one, we've got to look at the point 1. So at the point 1, the value is 2. So the limit, as we approach it from the negative side, the limit is 2. But as we approach it from the positive side, the limit is 3. I know it's crazy, but you can see what's happening. Let's have a look at the third one. We've only got to look at the point 1. So at the point 1, the value is 1. As we approach it from this side, the value approaches 1. As we approach 1 from this side, the value approaches 2. Okay, so look at some really annoying ones there. A, B, C, D, and E. So for each of the functions, state the value of x for which there is discontinuity and use the definition to explain why. So that definition that we looked at before. So here, greater than or equal to 0, less than 0. So we've got to check what's happening at 0. So f of 0 there is 0, isn't it? 2 times 0 is 0. Here, the value is 1. So we've checked it, and it's a different value. So it's discontinuous when x equals 0. B, so again, greater than or equal to 0, less than or equal to 0. So we've got to check 0. If x is 0, that's 0. If x is 0, that's 1. So it's discontinuity. This one here, less than or equal to 1, from 1 to 0, and greater than 0. So we've got to check a couple of points with C. So at -1, That's going to be -1. That's going to be +1. So we've already proven that there's discontinuity. The other point we've got to check is 0. So that's 0, that's the same. That's 0, that's the same. But if that's 0, that's going to be 1. So there's discontinuity there as well. D. So only checking 0. So 0 squared plus 1 is 1. 2 times that, so it's 1. So you get the same value there. So no discontinuity. And E, again, we're only checking 0. So that's going to be 0. That's going to be 0. So basically, you're just subbing in to see if you get the same answers or different answers, yeah? L'Hopital, 17th century French mathematician. So he got all the credit, but Bernoulli was the one that did it. Who knows? It was so long ago. Let's pick who do we think is the most handsome. We'll choose them to have it. Very difficult there, isn't it? I think they might even have shared a wig. What is his rule? So what he's saying is the limit of two functions will be the same as the limit of their differentiated functions. Can that at all be useful? What the hell? How on earth would he have come up with that? So sometimes the derivative is easier to work with. If you think about it, if we've got a cubic here, when we differentiate it, we're going to have a quadratic, aren't we? If we've got a quadratic here and we differentiate it, we're going to have a linear. So don't forget, when you differentiate something, you lose a power. So sometimes that does make it easy. Okay, let's work out the limit of this. So as x approaches 0, 0 times 0 is 0, plus if we get 0 on the bottom, so we've got a problem, haven't we? Let's see what happens if we differentiate it. So according to L'Hopital's rule, this will be the same as this. So we differentiate that stays the same, doesn't it? Differentiate that, it disappears. That's 2x plus 1. So now, when we substitute in, x is 0. Remember, we're approaching it when x equals 0. E to the 0, 2 times 0 is 0, plus 1 is 1. So we haven't got a 0 on the bottom. A to the power of 0 was 1. So the answer is 1. Seemed to have been helpful there. So the limit of this is 1. So here's a question. That one there. And I thought, oh, it's a bit of a pain, this one. So let's have a look at it. I'm trying to find the limit of that. Now the solution is factorize, cancel those two, substitute x equal 2 over that, and we get the answer 11/9. Let's have a look at what would happen if we use L'Hopital's rule. So we know that if we just substitute in for x equals 2, we get 0/0, so pain in the bum. So let's differentiate. If we differentiate the top, differentiate the bottom. Differentiate the top, 6x minus 1, differentiate the bottom, substitute in for x equal to 2, we get 11/9, same answer. Which way is better? You decide. So there's some notes. There's an Ed Rollo video. What about when is a function differentiable? So we've seen this before, haven't we? We know this formula here. For the function with the following rule, find f dash of x and sketch the graph of f dash of x. That doesn't sound too tricky. Differentiate it, sketch the graph. So if x is greater than 0, 2x plus 1. If x is less than 0, 2. And we've got the point 0.2 is where it joins, and it joins smoothly because we've got a greater than or equal to there, a less than there. So it's continuous. Here's another one. Find f of x and sketch the graph. So again, we're differentiating this, sketching the graph. Not as simple, this one, is it? Greater than or equal. So we've got 2x plus 2. And here we've got y equals 1. Now we know that that one's a circle because it's less than, but because we have discontinuity here, this is what the graph looks like. And this is the notation that you can use. Lots of other notation you can use. Function is differentiable for all r apart from 0. Okay, got a bit of an annoying function there. State when the derivative is defined and sketch the graph of the derivative function. So if we differentiate that times that, take away our power, here's our graph, and we can clearly see that there's no derivative when x equals 0. Section summary, not too many questions, but they are quite tricky, so please be thorough.